In the end, it was a mathematician who decided to take the world at face value. His working hypothesis was that nature appears complex because it is complex. Benoit Mandelbrot was born in 1924 in Warsaw, Poland, but his family took refuge in France in the years before World War II. During his education in Paris at the École Polytechnique and during his subsequent academic tenure in several French cities, Mandelbrot was thoroughly exposed to and immunized against the austere formalist approach to mathematics. Eventually, he moved to the United States to join IBM's laboratory for pure research. Throughout his career, Mandelbrot has cultivated an intuitive visual approach to the mathematical problems that interest him. He is attracted to problems that respond to this approach, and he believes open-mindedness is essential to scientific progress.
Science would be ruined if it were to withdraw entirely into narrowly defined specialties. The rare scholars who are wanderers by choice are essential to the intellectual welfare of the settled disciplines.
Mandelbrot is one of the wanderers. Especially in the earlier years of his career, he moved from one field to another, from economics to geology to physiology to botany, looking for interesting problems. He usually became interested in data that other scientists had ignored because it didn't display any obvious pattern or regularity. But frequently there was some hidden regularity. The data had a property called scaling. As we will see, this means that the irregularities are identical at all scales of observation. Scaling may appear unremarkable, but whether it's remarkable or not depends on your expectations. Mathematicians and scientists tend to divide phenomena into those with simple deterministic causes, which are described by physical laws of causation, and those with random causes, which are subject only to statistical laws. Scaling phenomena do not fit comfortably into either class, though at first sight they might appear to be random because they're extremely complex. Scaling relationships were already well established within some fields. Geographers, for example, have long known that in many countries, including the United States, the populations of cities, when ranked by size, often display a scaling relationship. This means that certain size ratios are constant. The largest city is roughly twice as large as the second largest, about 3 times as large as the third largest, and so forth. In the United States, this relationship has remained remarkably stable for 200 years, in spite of dramatic growth and change. Some cities, like Los Angeles, appear from nowhere and grow until they're among the largest in the world. Other cities, once important, become insignificant. But the scaling relationship remains constant. These scaling relationships were once considered curiosities, and they were not well understood. Mandelbrot realized that scaling relationships indicate patterns of a different sort, non-Euclidean patterns of great complexity. These patterns are, in the common sense of the word, natural or organic. As he puts it,
why is geometry often described as cold and dry? One reason lies in its inability to describe the shape of a cloud, a mountain, a coastline, or a tree. Clouds are not spheres. Mountains are not cones. Coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. More generally, I claim that many patterns of nature are so irregular and fragmented that nature exhibits not simply a higher degree, but an altogether different level of complexity.
He continues by describing a new class of shapes.
The existence of these patterns challenges us to study those forms that Euclid leaves aside as being formless, to investigate the morphology of the amorphous. Mathematicians have disdained this challenge, however, and have increasingly chosen to flee from nature by devising theories unrelated to anything we can see or feel. Responding to this challenge, I conceived and developed a new geometry of nature and implemented its use in a number of diverse fields. It describes many of the irregular and fragmented patterns around us and leads to full-fledged theories by identifying a family of shapes I call fractals. Scientists will, I'm sure, be surprised and delighted to find that not a few shapes they had to call grainy, hydra-like, in between, pimply, pocky, ramified, seaweedy, strange, tangled, tortuous, wiggly, wispy, wrinkled, and the like, can henceforth be approached in rigorous and vigorous quantitative fashion.
In spite of this fuzzy-sounding vocabulary, fractals are well-defined mathematical objects, but they can be appreciated intuitively as well. Mandelbrot describes them this way.
Fractals are geometrical shapes that, contrary to those of Euclid, are not regular at all. First, they are irregular all over. Secondly, they have the same degree of irregularity at all scales. A fractal object looks the same when examined from far away or nearby. It is self-similar. As you approach it, however, you find that small pieces of the whole, which seem from a distance to be formless blobs, become well-defined objects whose shape is roughly that of the previously examined whole. Nature provides many examples of fractals. For example, ferns, cauliflowers, and broccoli, and many other plants, because each branch and twig are very like the whole.
Mandelbrot is above all a mathematician. When he sees the same regularities or patterns in data from various scientific disciplines, he suspects that fundamental mathematical principles are involved. As it happens, many of the principles had been discovered a half-century or more earlier, but their significance had not been appreciated. Mandelbrot explains.
Indeed, while fractal geometry as such dates from 1975, many of its tools and concepts had been previously developed for diverse purposes altogether different from mine. Through old stones inserted in newly built structures, fractal geometry was able to borrow exceptionally extensive, rigorous foundations, and soon led to many compelling new questions in mathematics.
The mathematicians Giuseppe Peano of Italy and Georg Cantor of Germany were two people whose work helped Mandelbrot build his new geometry of fractals. Both had worked near the end of the 19th century. Peano constructed and analyzed a mathematical formula for a line that's so tortuously curved that it touches every point on a two-dimensional surface. It is now known as Peano's curve. Mandelbrot quotes three mathematicians who reacted in horror.
Vilenkin said, "Everything had come on strong. It is difficult to put into words the effect that Peano's result had on the mathematical world. It seemed that everything was in ruins, that all the basic mathematical concepts had lost their meaning." According to Hahn, Peano motion can not possibly be grasped by intuition. It can only be understood by logical analysis. And Dieudonné thought that some mathematical objects, like the Peano curve, are totally non-intuitive, extravagant.
Cantor created a similar monster by cutting the middle third out of a line, which leaves two shorter lines separated by a gap. He then cut the middle third out of each of these shorter lines, and so on, repeating the process indefinitely. Mandelbrot denotes these gaps by the word trema, a word that shares a root with the word termite. The contour set is a line that has been mostly eaten away, so only a sort of dust remains, and it is certainly a structure made in termite heaven.